Good morning, students. Today we will discuss about two topics: construction of single phase transformer, or we can say that types of transformer, and second topic is ideal transformer. So here there are primary two types of transformer. First one is core type transformer and second is cell type transformer. So we will start with core type transformer. Here is the arrangement of core type transformer. Here we can see in this figure that this rectangular part is core, but here horizontal part is yoke, and this two vertical part is called as limb. Here two windings are connected, primary winding and secondary winding. So first of all, core type transformer has single magnetic circuit. It has rectangular core with two limbs. This is rectangular core and these two are limbs, vertical limbs. Windings are wounded on limbs. Primary winding and secondary winding are wounded on limbs. Core is surrounded by the winding. This core is surrounded by the winding. It means winding is outer side, core is inside. Next, two vertical positions are limbs, each carry one half of the primary and one half of the secondary winding. These two vertical positions are known as limbs. These two horizontal sections are yokes. Here see in this figure, these two are yokes. Horizontal are yokes and vertical are limbs. This transformer, core type transformer, are low voltage winding is kept inside core and high voltage winding is placed on it. It means that low voltage winding, it means LV winding, is kept inside the core, but high voltage winding is placed on core. Okay. Here natural cooling is more effective. Coils can be removed. For repair easily because these windings are wounded on core, so it can be easily removed from core in core type transformer. And last one is construction is very simple. So these are the points for comparison with cell type transformer. Again I revise these important points. First of all, it has single magnetic circuit. It has rectangular core with two limbs. These two are limbs. Here windings are wounded on two limbs. Core is surrounded by windings. Two vertical positions are known as limbs and two horizontal positions are known as yokes. Here low voltage winding is kept inside the core, but high voltage winding is placed on it. Here we can see in the figure. Okay, natural cooling is more effective and we can easily remove this winding from the core. And last one is construction is simple. So these all are about core type transformer. Now we will discuss cell type transformer. In cell type transformer, see in the figure, these are core. This is primary winding and this is secondary winding. See, compare this figure with this. Here two limbs, but in cell type transformer there are three limbs. 1, 2 and 3. This is the central limb. In middle of this figure is central limb. These are yoke and this is side limbs. These two are side limbs. Okay. First of all, in cell type transformer has double magnetic circuit. Compare this. It has single magnetic circuit. Here double magnetic circuit. Core has three limbs and two yokes. These are three limbs and these are two yokes. Here primary and secondary windings are wounded on central limbs. So primary winding and this is secondary winding are wounded on central limbs. These cell type transformer is used for high voltage application. Here I have not mentioned, but it is the point for comparison. This core type transformer is used for low voltage applications. Here this cell type transformer is used for high voltage applications. Here natural cooling doesn't exist because windings are surrounded by core. Here windings outer side and core is inside. But in this case, core is outside and winding is inside. So natural cooling doesn't exist as windings are surrounded by core. Here we cannot easily remove that winding compared to this core type transformer. For removing any winding for repair, large number of laminations need to be removed. It means that we cannot easily remove that winding from the core in cell type transformer. Okay. Here coils are multi-layer disc type or sandwich coils, whereas in this rectangular coils are used. So cell type transformer, you have to keep in mind these important points. Again I repeat, it has single magnetic circuit, it has double magnetic circuit, it has two limbs, it has three limbs. Here central limbs are present. Here primary winding and secondary winding are on different limbs, but here primary and secondary winding on central limbs. Here we can easily remove the windings. We cannot easily remove the windings from the core. Natural cooling is present. Natural cooling is not present. Okay. So these all are about types of transformer, or we can say that topic as construction of single phase transformer. Okay. Now we will discuss about ideal transformer. So here so first of all, ideal transformer. What is the definition of ideal transformer? So the transformer in which no energy wasted in core and in winding is called ideal transformer. We can say that in ideal transformer there is no losses, there is no energy losses, or there is no energy wasted in main two parts. One is core and other is winding. So ideal transformer has following properties. Here these four are properties of ideal transformer. See here. It has no winding resistance. It has no leakage flux. Leakage flux means the same flux links with the both windings. We know that when we give alternating voltage to primary winding, it generates flux through it, and the same flux, total flux generated in primary winding, that whole flux link with secondary winding. There is no leakage flux. It has no iron losses in the core. Working efficiency is 100%. So these four are properties of ideal transformer. Again, I repeat, what is ideal transformer? The transformer in which no energy wasted in core or winding, or we can say that there is no energy losses in this type of transformer, and it has these four properties. It has no winding resistance, it has no leakage flux, it has no iron losses in core, and its working efficiency is 100%. Now we will discuss about operation and phasor diagram of ideal transformer. See in the figure, this is circuit diagram of ideal transformer and this is phasor diagram of ideal transformer. So first of all, it is not realized practically. Ideal transformer doesn't exist, but study of this ideal transformer provides a very powerful tool in a practical transformer. We will discuss in the next lectures about practical transformer, but this study of about ideal transformer provides us a good knowledge to study or to analyze practical transformer. So first of all, as we know that it consists of two coils. These two are coils, these two are windings, and these two windings are wounded on the core. So it consists of two coils. The windings connected to AC voltage V1, primary winding, is known as primary winding. So primary winding is connected to the AC voltage V1 and number of turns in primary winding is N1. And the winding which is connected to load is secondary winding. This winding which is connected to output or load, it is known as secondary winding. So first of all, we know that when primary winding is connected to voltage V1, the current Im flows through it. The current Im flows through it. When we provide voltage V1 to primary winding, current Im flows through it. Since primary coil is purely inductive, current Im lags voltage V1 by 90. So remember, in purely inductive circuit, we know that current Im lags V1 by pi by 2. Okay. Now, due to that Im, flux is produced in primary winding and it also linked with secondary winding. As we have discussed that in ideal transformer, there is no leakage flux. It means the whole flux generated by primary winding is linked with the secondary winding. So we can say that EMF E1 and E2 are induced in primary and secondary winding respectively. Both these EMF E1 and E2 are in same direction. See in the phasor diagram. But according to Lenz's law, we know that EMF produced opposes the cause of it. So we can say that E1 is equal but opposite to V1. That EMF E1 produced in primary winding is equal to V1 but exactly in opposite direction as per the Lenz's law. Now, in secondary winding, E2 is produced. E2 is also in antiphase with V1. E2 is also in antiphase with V1 because E2 is also produced due to V1. So it is also in opposite direction to the V1. Now, according to Faraday's law, we know that EMF in secondary coil E2 is given by minus N2 d phi by dt. As we discussed in previous lecture, this phi is nothing but phi m sin omega t. So I have directly written this differentiation. If we put phi equals to phi m sin omega t, by differentiating this phi m sin omega t with respect to t, we have minus n2 phi m omega cos omega t. And we can write sin omega t in place of this sin cos omega t in place of this sin omega t minus 90. So we have finally the equation of EMF induced in secondary winding. E2 is N2 phi m sin omega t minus 90. This indicates that this E2 EMF induced in secondary winding lags this phi by 90 because here omega t minus 90. It means that E2 induced in secondary winding lags flux by pi by 2. That's why E2 is here. So we can say that E2 lags flux phi by 90. So it is about ideal transformer. Again I revise this. So first of all, here ideal transformer, two windings. First winding is connected to V1 and second winding is connected to load. Here when we applied voltage in primary winding V1, then flux produced through it. we know that in ideal transformer, this whole flux linked with the secondary winding. Here, EMF produced in primary winding is equal but in opposite to V1 as per the Lenz's law. Now, EMF also induced in secondary winding. This EMF is given by E2. E2 and E1 are both in same direction. Okay. Here E2 is given by minus N2 d phi by dt. When we put phi equals to phi m sin omega t in this equation, we have finally equation of EMF induced in secondary winding E2 is equal to N2 phi m sin omega t minus 90. So that's why we can say that EMF induced in secondary winding leaks this flux or current by 90. So this is all about ideal transformer. Thank you.